Thanks for the introduction. Good afternoon. My name is Daniel Sepúlveda, and today I will present the progress of my research, Cenozoic Paleoclimate signals from Antarctica and the Andes, insights from clumped isotopes. This presentation covers two projects. The first investigates climate evolution from the Late Cretaceous to the Late Eocene in the Antarctic Peninsula, while the second focuses on the Miocene climate changes in the southern Patagonian Andes. Studying past climates provides crucial insights into the long-term relationship between atmospheric CO2 temperature and ice sheet stability. From the Late Cretaceous to the Eocene, Earth transitioned from a warm phase ice-free world to the onset of the Antarctic glaciation. During the early Eocene, CO2 levels peaked approximately 1,600 ppm, driving global temperatures 12 degrees higher than today. A long-term trend cooling followed by the Eocene-Oligocene transition. 34 million years ago, CO2 levels had declined to 720 ppm, triggering the formation of the first Antarctic ice sheets. This epoch served as a natural record of climate response to CO2 changes, improving our understanding of ice sheet stability, sea level rise, and climate sensitivity, key factors in predicting future climate change. Seymour Island in the Antarctic Peninsula preserves an exceptional geological and paleontological record of high-latitude environmental changes. Its continuous sedimentary sequence spanning the Late Cretaceous to the Eocene makes it ideal for reconstructing past climate conditions. The tectonic evolution of the region was driven by the subduction of the Phoenix plates beneath the Antarctic plate, shaping basin development and sedimentation patterns. During the Late Cretaceous, subduction formed a back arc basin where the Lopez de Bertolano Formation accumulated. In the Paleocene, increased volcanic activity contributed to the deposition of Sobral and Cross Valley Formation, with record of estuarine and lagoon environments influenced by episodic sediment influx. By the early to middle Miocene, uplift and basin reorganization led to the incision of La Meseta Formation. In the Late Eocene, the final phase of Phoenix plate subduction ended, coinciding with the opening of the Drake Passage, a deep water gateway between South America and Antarctica. These events altered ocean circulation, driving global cooling and the onset of the Antarctic glaciation. Before discussing previous paleoenvironmental records, I will introduce key concepts in stable isotope geochemistry. Delta 13C refers to the ratio of carbon 13 to carbon 12 in a sample relative to a standard, Vienna PD belemnite. In the marine realm, Delta 13C is a crucial indicator of global carbon cycle, as changes in its values reflect in organic carbon burial, ocean circulation, and biological productivity. Higher Delta 13C values indicate increased carbon burial, while lower values suggest remineralization or changes in water mass composition. The Delta 18O, on the other hand, measures the ratio of oxygen 18 to oxygen 16. In carbonate minerals, Delta 18O is influenced by seawater temperature and the isotopic composition of the water from which they precipitate. Higher carbonate Delta 18O values correspond to cooler conditions, as heavier isotopes are preferentially incorporated into carbonate minerals at lower temperatures. Conversely, lower Delta 18O values indicate warmer temperatures. Delta 18O in seawater is a valuable tool for understanding hydrological changes, including ice sheets, formation and melting, ocean circulation patterns, and variations in global precipitation and evaporation. During glacial periods, ice sheets preferentially store lighter isotopes, increasing Delta 18O values in seawater. Conversely, melting ice sheets release lighter isotopes back into the ocean, decreasing Delta 18O values. Together, Delta 13C and Delta 18O provide a comprehensive picture of past environmental conditions. The geological record preserves these values in various materials, including marine fossils such as bivalves, brachiopods, and foraminifera. These organisms incorporate delta 13C and delta 18O into their carbonate shells during growth, making them valuable archives for reconstructing past oceanic and climatic conditions. Paleoclimate reconstructions from Seymour Island reveal a cooling trend from the Maastrichtian to the Eocene and with Kempf et al. Estimated mean annual temperatures of 12.4 degrees Celsius in Lopez de Bertolano Formation, while Scasso reported slightly higher values of 16 degrees Celsius using the MBT-CBT paleothermometer, a geochemical proxy based on bacterial lipids biomarkers. Ferreira et al. Found evidence of warm, humid conditions during this period through palynological and geochemical analysis. In the Paleocene, mean annual temperatures remain at 12.4 degrees Celsius in the Soral Formation, according to Kempf et al., but gradually cooled, as indicated by Ferreira et al. By the Paleocene, cooling intensified and temperatures declined, showing an average of 8.7 degrees Celsius in the Cross Valley Formation. For context, the mean annual temperatures on Seymour Island, modern temperatures are of negative 2 degrees Celsius as recorded in the Marambio station about 4 miles from the island. This figure by Kempf et al. Shows a stratigraphic column and the MBT-CBT derived temperatures across the Maastrichtian Paleocene transition. The KPG boundary marks the shift from the Lopez de Bertolano and Sobral Formation and Cross Valley Formation. Temperature estimates represented by orange squares indicate warm conditions in the Maastrichtian, followed by a slight cooling trend in the Paleocene for the temperature drop in the late Paleocene. This trend reflects a gradual cooling after the KPG boundary. Stable isotope records from Seymour Island provide insight into past carbon cycle variations. Barrera et al. Analyzed delta 13C values from benthic foraminifera and Lopez de Bertolano Formation, noting fluctuations corresponding to paleotemperature changes. Later, Gatsitsky et al. Identified about 6 per mil negative delta 13C shift in La Meseta Formation, potentially reflecting increasing terrestrial organic input or a shift from a stratified to a more mixed ocean, coinciding with a broader cooling trends. Tobin and Ward observed that ammonites exhibited lower delta 13C values than benthic mollusks with an offset of 4 per mil due to metabolic effects. A sharp negative delta 13C excursion at 3 per mil at the Cretaceous Paleogene boundary correspond to a global carbon cycle perturbation linked to mass extinction. Regarding oxygen isotope records, Barrera et al. Analyzed delta 18O values from benthic foraminifera, reporting carbonate delta 18O averaging 0.2 per mil ppb. Assuming an ice-free world, they inferred seawater delta 18O averaging negative 1.5 small, indicating warm high latitude conditions influenced by ocean circulation. Gatsitsky et al. Found fluctuations between 0 and 3 in the La Meseta Formation, consistent with a cooling trend linked to early Antarctic glaciation. In the next few slides, I will discuss how clumped isotopes and delta 13C and delta 18O analysis provide insights into past climates and environmental changes in the Antarctic Peninsula, specifically focusing in the Seymour Island. This research aimed to reconstruct temperature variations, carbon cycle shifts, and hydrological changes during key climatic transitions, such as the Cretaceous Paleogene boundary. To achieve this, we used a multi-method approach. First, we selected and screened fossil specimens to ensure well-preserved samples for analysis. Then we conducted stable isotope analysis, focusing on isotopic ratios. The isotope thermometry was applied to reconstruct past temperatures. Finally, by integrating these datasets, we developed a comprehensive climate reconstruction that enhances our understanding of high-latitude climate dynamics in a greenhouse world. Bivalve fossil shells composed primarily of calcium carbonate serve as valuable archives for reconstructing climate conditions. The oxygen isotope composition of bivalve shells is influenced by both the water temperature and the delta 18O of dissolving organic carbon in the fluid between the mantle, the tissue that secretes calcium carbonate, and the inner shell surface, where biomineralization occurs. Similarly, delta 13C serves as reflects a combination of environmental dissolving organic carbon, DIC, and metabolic contributions. While delta 13C in carbon is not typically used to reconstruct DIC directly due to biological influences, it still serves as an indicator of large-scale changes in the carbon cycle and primary productivity. For this study, we use fossil bivalve shells and gastropod samples obtained from previous collections, representing well-preserved marine shallow community from the 4 geological formations I previously mentioned. Clumped isotope geochemistry provide a direct method for reconstructing past temperatures by analyzing the preferential bonding of heavy isotopes within carbonate molecules. In carbonate system, the mass 47 isotopologues of carbon dioxide deviate from stochastic distribution due to thermodynamic effects. This deviation is quantified as capital delta 47 value, which serves as a reliable paleothermometer, independent of the isotopic composition of the parent water. Unlike delta 18O, base temperature reconstructions will require assumptions about the past delta 18O water values. Clumped isotope thermometry directly measures mineral formation temperatures. The analysis begins with digesting the powder carbonate samples in phosphoric acid, releasing CO2 gas. This gas is purified using cryogenic traps and gas chromatography to remove contaminants before being analyzed via isotope ratio mass spectrometry, IRMS. The mass spectrometer separates the ionized CO2 molecules based on their mass to charge ratio, allowing precise measurements of isotopic abundances. These results are standardized using an interlaboratory calibration framework, the intercar carbon dioxide equilibrium scales. The final capital delta 47 values are converted into temperatures using an empirical calibration, such as the one by Anderson et al. Advancements in the past few years have greatly improved the reliability of clumped isotope thermometry, making it an essential tool for reconstructing past climate and geological conditions. Our delta 13C results show a gradual decline from the late Cretaceous through the Paleocene, a temporal enrichment in the early Eocene, and a negative shift in the middle Miocene, and a partial recovery in the late Eocene. These findings align with and extend previous studies. Kaczynski reported a negative shift in the middle Eocene, which matches with our data and supports the hypothesis that enhanced ocean mixing disrupted the carbon cycle. Our results build on the work of Barrera et al., confirming delta 13C values fluctuating between -2 and +2 per mil VPDP from the late Campanian to the early Paleocene, while capturing additional variability later in the Eocene that the previous studies did not document. In contrast with Tobin and Ward, who observed specific species delta 13C differences between ammonites and benthic mollusks, our results focus on the long-term environmental trends, demonstrating that delta 13C fluctuations were linked to broader climate and ocean circulation changes rather than metabolic effects. The recovery of delta 13C values in the late Eocene suggests a period of stabilization before the Antarctic glaciation, reinforcing the transition from a greenhouse to icehouse world. The delta 18O of carbonate records shows variability, but increasing trend towards the late Eocene. In the late Cretaceous, delta 18O values were relatively low, averaging 0.28 per mil VPDV, an increase in the early Paleocene to about 0.7 per mil, suggesting environmental reorganization following the KPG boundary event. The late Paleocene and the early Eocene delta 18 values remain variable, reflecting the dynamic oceanographic conditions. A more pronounced shifts occurred in the middle Eocene, where delta 18O values decline, become more negative before rising in the late Eocene, averaging about 1.5 per mil. A pattern consistent with the onset of cooler conditions. These findings align with Barrera et al., who reported delta 18 values of 0.2 per mil, whereas we found 0.28 per mil. They also documented a standard deviation between 0.2 to 0.6 per mil, while we reported 0.07 per mil, indicating a significant reduction. This suggests improved analytical precision and refined methodologies, contributing to a more reliable isotope ratio reconstructions in the late Cretaceous. Additionally, we observed a similar delta 18O trend in the Eocene in the La Meseta formation, consistent with Gatsinski, who documented delta 18O increases in the Eocene linked to potential Antarctic glaciation. The delta 18O of seawater reveals major climatic and hydrological shifts. Values were low in the late Cretaceous of negative 1.2 per mil VSMO, similar to the negative 1.5 VSMO reported by Barrera et al., but increased through the Paleocene, peaking in the late Paleocene, likely due to changes in ocean circulation and precipitation, and decline in the early Eocene suggests a shift in the global hydrological cycle, while stable middle Eocene values indicate warm but steady conditions. By the late Eocene, delta 18O rose again, marking a cooling and possible ice sheet expansion, aligning with broader climate trends. Around 34 million years ago, we observed a sharp increase in delta 18O seawater values, which may be related to the OE1 event, a potential precursor signal due to a major pulse of Antarctic ice sheet formation. This finding agrees with previous studies on foraminiferous samples from the equatorial Pacific conducted by Lear et al. 2004. The temperature history of Seymour Island reveals significant climate fluctuations. During the Maastrichtian, temperatures were relatively cool, averaging 10.5 plus minus 5.1 degrees Celsius, which is 2 degrees Celsius lower than the values reported by Kempf et al. A warming trend followed in the early Paleocene, with temperatures reaching approximately 15 degrees Celsius, likely influenced by the post-KPGE climatic shifts. This is slightly higher than the temperatures reported by Kempf et al. Of 12.4 degrees Celsius. Temperatures remain stable through the late Paleocene before increasing slightly during the early Eocene, a well-documented greenhouse period. Big warm occurred during the middle Eocene, about 20 degrees Celsius, coinciding with major carbon cycle disruptions. By the late Eocene, temperatures had begun to decline, dropping approximately to an average of 11 degrees Celsius, marking the transition to ice house conditions and the onset of early Antarctic glaciation. Our study confirms significant high latitude climate variability in the Seymour Island from the late Cretaceous to the late Eocene, with temperatures fluctuating between 10.5 degrees Celsius in the Maastrichtian, peaking at about 12 degrees Celsius in the middle Eocene, and cooling about 11 degrees Celsius by the late Eocene. These trends align with major climate trends and with major climate events, including the transition from a greenhouse to an ice house world. The warming phase in the early Paleocene suggests rapid environmental adjustment after the KPG boundary, while the Middle Eocene peak reflects intensified greenhouse conditions before a long-term cooling trend cooling set in. The Delta 13C records exhibit a negative shift in the Middle Eocene, likely due to an increased ocean mixing and carbon cycle disruptions. Meanwhile, Delta 18 of carbonate progressively rise, indicating cooling and potential ice sheet expansion. Changes in Delta 18O seawater suggest shifts in regional precipitation and ocean circulation, underscoring the sensitivity of Antarctic climates to global climate drivers. These results provide valuable paleotemperature data that refine climate models and contribute to future research on the stability of polar environments in response to past and future warming. Future research will focus on enhancing the resolution and accuracy of our data by increasing sample replication. Another objective is to investigate ancient seasonal climate variability using high-resolution clumped isotope thermometry combined with stable isotope analysis across different time intervals in selected taxa. This approach will provide a more detailed understanding of short-term climate changes in ancient environments. A critical aspect of future work involves assessing fossil preservation to ensure that isotopic data accurately reflect the original environmental conditions. Advanced screen techniques such as cathodoluminescence and trace elements will be employed to identify pristine carbonate samples and distinguish primary climate signals from post-depositional alterations. Comparisons with high latitude and mid-latitude paleoclimate records will help to contextualize Seymour Island's climate history within global climate trends. This approach will contribute to a broader understanding of polar amplification and its role in past greenhouse climates. A crucial next step is to compare our reconstructed paleotemperatures with climate model simulations to evaluate how well current models replicate past greenhouse climates. The second part of this talk examines climate evolution during the Miocene epoch in the southern Patagonian Andes. The Miocene epoch, which lasted from 23 to 5 million years ago, was a period of significant climate variability. One of the most notable warm phases was the Miocene climatic optimum between 17 and 15 million years ago. This was followed by a cooling phase known as the Middle Miocene climatic transition, or MMCT. During this time, atmospheric carbon dioxide levels ranged approximately between 400 and 600 ppm, and global temperatures were comparable to projections in the near future. Because the configuration of the continents and ocean circulation patterns were already similar to today's, the Miocene serves as an important climate analog. Studying this epoch helped us refine future climate projections by providing insights into how Earth's climate system responds to elevated CO2 levels. The study area is located in the Patagonian Andes, Argentina. Research focuses in the Santa Cruz Formation, a key archive of early to middle Miocene and high latitude paleoenvironments, paleoclimates, and terrestrial ecosystems in the southern hemisphere. Unlike the northern hemisphere, where terrestrial paleotemperatures proxy for these periods are more abundant, the southern hemisphere has a scarcity of such records, making this formation particularly valuable. The Santa Cruz Formation consists of diverse lithologies, including tubaceous deposits, fine-grained sedimentary rocks, such as claystone and mudstone and sandstone. The Cenozoic uplift in this region has been driven by two major oceanic ridge subduction events beneath the South American plate. The first occurred in the Paleogene, when the Aluk spreading center subducted beneath South America, followed by the ongoing subduction of multiple segments of the Chile Ridge beginning about 15 million years ago. The study area located in the foreland basin of the Andes preserves evidence of these tectonic events, including mountain uplift formation of the rain shadow, and associated climatic shifts. These changes led to increased aridity and significant shifts in vegetation during the Miocene, fundamentally altering the regional landscape. The interplay between tectonics and climate highlights how geological processes shape regional environments and influence long-term ecological and climatic evolution. Surface uplifts plays a crucial role in shaping and climate and ecosystem, affecting erosion, sediment transport, and deposition. This influence is especially strong in mountainous regions where topography creates sharp climatic difference. In the Andes, which rise 3.7 kilometers, the mountains block the westerly winds, leading to one of the most extreme orographic rain shadows on Earth. The western side receives over 3,000 millimeters of rainfall per year, supported humid environments, while the eastern side receives as little as 300 millimeters annually, creating arid conditions. Rayleigh distillation plays a crucial role in shaping the isotopic composition of precipitation across the Andes. As moist air masses rise over the mountains, progressive fractionation occurs, leading to the depletion of heavy isotopes 18O in precipitation. As air ascends, it cools and condenses, causing precipitation to be enriched in 18O, the heavy isotope of oxygen, while remaining vapor becomes progressively depleted in heavy isotopes. By the time air reaches the leeward side, delta 18O values in precipitation are significantly lower due to continuous isotopic fractionation. This steep topographic gradient in the Andes enhances this process, reinforcing strong delta 18O depletion in precipitation and surface waters, particularly on the eastern slopes. Delta 13C variations in vegetation provide key insights into past environmental changes as they distinguish between C3 and C4 plants with different photosynthetic pathways. C3 plants, including trees, shrubs, and temperate grasses, rely on the Calvin cycle, which preferentially excludes 13C, resulting in delta 13C values between negative 30 per mil to negative 22 per mil. In contrast, C4 plants, such as tropical grasses, some sedges, utilize the Hatch-Pass pathway, leading to delta 13C values ranging from negative 14 per mil to negative 10 per mil. A transition from C3 to C4 dominance often reflects increasing aridity and temperature. The integration of clumped isotope thermometry and delta 18O of water has significantly refined paleoclimatry, allowing more accurate reconstructions of past elevations. Studies in Central Andes by Garcione et al. And in the Tibetan Plateau by Huntington et al. Demonstrated rapid uplift events and confirmed that capital delta 47 provides critical paleotemperature data, which combine with delta 18O lapse rates, offering robust elevation estimates. However, concerns over diagenetic resetting and climatic influences on isotopic values underscore the need for careful interpretation using multi-proxy approaches. This figure by Moog 2016 illustrates two paleotimetry methods. In A, delta 18O decreased with elevation as the orographic gradient influenced climate shifts. In B, the delta approach, comparing delta 18O between lowland and highland sites to separate uplift from climate effects. In the southern Patagonian Andes, the combination of capital delta 47 derived temperatures and delta 18O lapses is crucial for reconstructing past elevations, especially given the region's strong rain shadow effect. Westerly winds cause a significant delta 18O water depletion on the windward side, creating stepped isotopic gradients that must be considered in paleotimetry studies. This study is guided by three primary research questions. First, we aim to understand Miocene temperature variations in Patagonia. Second, we examine paleoenvironmental signals preserve in stable isotope geochemistry. Finally, we investigate the paleochemistry of the southern Patagonian Andes. Together, this question helps reconstruct past climatic and environmental conditions, shedding light on the geological and climatic evolution of Patagonia. Fieldwork was conducted on a 500-meter sedimentary section of the Santa Cruz Formation near Lago Posadas. Its control was established using argon-argon dating on intercalated volcanic layers, confirming the position between 22 and 14 million years. Collaborators collected carbonate nodules from Paleozoic horizons ranging from 5 millimeters to 3 centimeters in size. These nodules were ultrasonically cleaned, crushed, or drilled to obtain powder for isotopic analysis. Paleozoics are ancient soils that preserve past climate and environmental conditions, recording interactions between the Earth's spheres. Their physical, chemical, and biological indicators make them essential for reconstructing paleoclimate, hydrology, and vegetation dynamics. Previous research has examined the impact of Andean uplift on climate and vegetation shifts. In Patagonia, Blixnuk et al. Investigated how Miocene uplift intensified the rain shadow effect, contributing to increasing aridity and the transition from humid forest to dry steppe environments. The analysis of delta 13C and delta 18O variations in Paleozones revealed progressive shift toward more arid, adapted vegetation, and decrease in delta 18O values consistent with higher elevations. Building on this, Metzer 2013 analyzed Paleozones from the Santa Cruz Formation to refine Miocene climate reconstructions. This study identified a shift in soil types, showing that early Miocene environments supported grasslands and open shrublands, while the middle Miocene soils reflected increasing aridity. Later, Trailer et al. Analyzed delta 18O and delta 13C from herbivore tooth enamel in the Santa Cruz Formation to assess environmental changes during the Miocene climatic optimum. Delta 13C values indicate a C3-dominated ecosystem with mixed wooded and open areas. Delta 18O values reveal warming trend with estimated temperatures rising from 20 degrees Celsius at 17.4 million years ago and to 25 degrees Celsius by 16.4 million years ago. These findings highlights significant warming in Patagonia and suggest that climate models may underestimate Miocene temperatures in this region that currently have temperatures of about 8 degrees Celsius. Preliminary delta 15C results show a progressive increase from the early Miocene to middle Miocene, suggesting an increase in aridity and a shift in vegetation. Delta 13C values rise from an average of negative 10.2 per mil VPDV in the early Miocene to negative 9.5 per mil during the MCO, reaching negative 8.5 per mil in the middle Miocene. This pattern indicates transition from more humid forests dominated by C3 plants to increasingly open landscape with greater presence of C4 vegetation. These trends align with Blixnuk et al., who observed at about 3 per mil increase around 16.5 million years ago, linking to the Andean uplift, which intensified the rain shadow effect on the eastern foreland and contributed to increasing aridity. However, delta 13C values suggest greater aridity. The presence of significant C4 vegetation may not have fully developed until later. Delta 18O carbonate record reflects significant climate and tectonic shifts in the southern Patagonia Andes. In the early Miocene, delta 18O values average negative 12.1 per mil VPDV. During the MCO, values declined to an average of negative 12.7 per mil VPDV, suggesting cooling and shifts in precipitation patterns. These findings align with Blixnuk et al., who reported at about 2 per mil delta 18O carbonate decrease around 16.5 million years ago, attributing to about 1 kilometer Andean uplift and intense aridification. The continued depletion into the middle Miocene suggests a restrengthening ray shadow effect, while declining atmospheric CO2 levels may have further contributed to a drier and cooler climate. The Delta 18O water data reveal a trend of progressive depletion, reflecting hydrological changes in the region. In the early Miocene, Delta 18O average negative 9.6 per mil V small, remaining relatively variable during the MCO, with values averaging negative 9.7 per mil V small. By the middle Miocene, Delta 18O water values decline to negative 10.7 per mil V small, suggesting rising elevations, intensified rain shadow effects, and shifts in atmospheric circulation. Clumped isotope derived temperatures further clarify Miocene climate trends. In the early Miocene, temperatures average 26.3 degrees Celsius, peaking at, and in the MCO at 27.2 degrees Celsius. By the middle Miocene, temperatures declined to 24 degrees Celsius, reflecting a cooling trend alongside increasing aridity. This trajectory suggests initial warming during the MCO, followed by a long-term cooling and drier conditions consistent with broader climate shifts during the Miocene. Our temperature trend agrees with global trends and other continental temperature changes within the same time frame, derived from clumped isotopes in paleosols at other latitudes. For instance, a study by Mettner et al. 2020 reported similar trends at 25 degrees north in Switzerland. The key takeaways of this study highlight how climate and tectonic forces shape the Miocene environment in Patagonia. Delta 13C record indicates increasing aridity, likely driven by Andean uplift, which enhance the rain shadow effect and influence vegetation shifts toward drier adapted plants. The Delta 18O carbonate records show gradual depletion, suggesting hydrological changes, elevation shifts, and evolving moisture sources. The Delta 18O water records supports the idea of rising elevations due to Andean uplift, modifying the Delta 18O values and precipitation and contributed to drier conditions to the east of the mountains. The temperature data show peak warm in the MCO, followed by a cooling trend decreasing to 24 degrees Celsius in the middle Miocene, reflecting both global climate shift and regional tectonic influences. While this study provides new insight into Miocene climate evolution and the Andean uplift, further research is needed to refine interpretations. Expanding sample coverage and increasing replication will improve isotopic resolution. A multi-proxy approach integrating additional climate indicators such as biogenic silica, clay mineralogy, and fossil pollen records will offer a more comprehensive picture of environmental change. Comparing terrestrial record with marine climate data will help evaluate how global climate trends, including the Miocene climatic optimum and the Miocene cooling influence, mid-latitude regions of the southern hemisphere. Refining Delta 18O water elevation relationship specific to Patagonia will be also crucial. Incorporating modern precipitation Delta 18O water dataset will help to calibrate models of the Miocene atmospheric circulation and uplift rates. Comparing these results with climate model simulations will further assess the role of CO2 levels and the Andean uplift in shaping temperature and precipitation gradients. General circulation models, GCMs, will be essential in evaluating climate tectonic feedbacks and refining predictions for future climate change. Addressing this aspect will enhance our understanding of climate reconstructions, Miocene climate reconstructions, and refine Andean uplift estimates, and will improve our understanding of long-term climate evolution in the southern hemisphere. I would like to express my gratitude to my collaborators, the members of our lab, Team Star Wars, and the institutions that supported this research. That concludes my presentation. Thank you very much for your time.